Hello everyone, welcome back to our weekly lecture series from the Center for Compressor Technology. Today we are diving into something that sounds complex, but is truly the backbone of designing efficient compressors. It's the transformation matrices. This sounds fancy, right? Well, let me show you how they make rotor motion not just possible, but precise and optimized in compressor design. Let's start with the basics. Imagine two rotors in their local coordinate systems. These systems help us track the motion, position, and interaction between two rotors in a compressor machine. But here's the challenge. Those rotors don't stay static. As you can see, they are constantly rotating and moving in relation to one another. So how do we keep track of that movement? The answer lies in transformation matrices. In this example, we are looking at internally geared screw machine, but the same principle is applied to the conventional twin screw machine. We have local coordinate system fixed to the inner rotor or main rotor, which I'll call S1, and another coordinate system which is fixed to the outer rotor. I'll call that one S2. We also have a global coordinate system called SF. S1 and SF share the same origin, while S2 has its own origin at the center distance E. The trick here is to convert the points from S1 to S2 or SF or the other way around. That's where the transformation matrices come in. Now, what exactly is a transformation matrix? Well, to simply put, it's a mathematical tool that allows us to shift from one coordinate system to another. But for us, this means we can easily translate between the local movement of one rotor and the global motion of the entire compressor system. Without it, we'd be stuck trying to track every point on the rotor manually, which is way too complex. Each time the rotors rotate, a transformation matrix, let's say a two-dimensional one, helps us map the position of the points from one rotor onto another. This not only ensures that the rotors mesh perfectly, but also allows us to design their profiles with extreme accuracy. In every design of compressor system, we start by defining a gearing ratio, a radii of pitch circles, and axis distance. Structure of 2D transformation matrix from S1 to S2 coordinate system is dependent on angle between the rotors and axis distance E. First part of the transformation matrix represents rotational motion, and the second part represents translation. If we want to transform points from one coordinate system, from S1 to S2, we simply multiply points by this matrix. For practical benefits, in presented animations we can see how we can use transformation matrices to envelope one rotor from another one. Why does this matter for compressor design? Well, simply, accuracy equals efficiency. If we know the exact position of each point on the rotor as it moves, we can optimize the contact between the rotors, reduce leakage, and maximize compressor efficiency. These matrices also allows us to simulate motion before we even build the rotor, which is saving us both time and resources in the design phase. So to wrap it up, transformation matrices may sound intimidating, but they are a crucial tool that gives us control over the motion of our rotors. They transform complexity into clarity, ensuring our designers are not just functional, but optimized for maximum performance. Well, that's why mastering them is a key to mastering rotor design. Thanks for tuning in for today's lecture. Next time you're thinking about how those rotors spin so perfectly together, remember, transformation matrices are making that magic happen. See you next week.